We are on our last major logical skill. You have done it. You are almost there. This last one is, I know this is going to come as a shock to you, really fun. We are now getting to do actual proofs. It's very rare that even in math we get to do an actual proof, but these are literal proofs we are getting to do. Let me show you what's happening. So we are doing what are called deductive derivations, or I simply just call them deductive proofs. We are doing proofs in logic. The other way to think of this is think that we are now thinking in our logical language. We are thinking inside SL. Instead of looking at an English argument and then using SL to test it, think of this as using SL to think logically step by step. Instead of testing to make sure we're being logical, we will simply think logically. We will connect our thoughts up one thought at a time, following the logic of SL's rules, so that we are sure that each move we make is logical and true. Now, go for a basic example. Think of this. Now, we always start with some kind of goal. Remember, I am like a puppy. I am very much food motivated. Anything I'm trying to get myself to do, if the reward is food, I will do it. When I record these lectures, there is some food standing by over there that I get to eat if I finish making this video. That's how I work. So, let's say that my goal tonight is to get some pie. Oh, like key lime pie or lemon pie or something like that. So my goal is pie. Well, let's see if I can logically deduce whether I will get pie. So, what do I know? We always start our thinking with a certain set of assumptions. We will call these our premises. Well, what do I know? I know that my goal is to get pie, and then my premises are, I know that if we go out to dinner, then I will get pie. We don't have pie at home, so I have to go out to dinner to get it. And what else do I know? My wife just told me that we are going to go to the movies and to dinner. Right? Let's imagine this isn't during COVID. Let's imagine the vaccine is here. So I know two things in my premises. I know that if we go out to dinner, I'll get pie. And I know that we're going to the movies and we're going to dinner. Well, what logically follows from that? Well, I know that if we're going to the movies and going to dinner, we're going to dinner. And if we're going to dinner, I get pie, therefore I get pie. Do you see how it works? We used good logic to move step by step from our premises to our goal, and I can prove that my goal follows from those premises. All right. So, but instead of using just basic common sense, now that was common sense, and what I did was actually fully deductively logical. But in order to make sure we're doing that, we will produce each line based on the rules of deductive logic. Instead of just using common sense that could mislead us, we are going to make sure that each step in our proof, each thought in SL, follows from a logical deductive rule. So, and let me show you the basics. Let's give some analogies for this. In a rough way, it is like citing data in a paper. You're doing work in economics or biology or chemistry or something. Well, you need to cite the data to make sure the steps you are making do follow from the rules. Let's go a little closer to what we're actually doing. Think of following the traffic rules. Now, we have those in our brains mostly unconsciously, but imagine you are pulled over by Popo. If you are pulled over, you should be able to justify what you've done by the rules, or else you do get a ticket. So, for example, let's say I turned on a red light. I turn on a red light, now I could just with common sense say, oh, I did it safely. No, that's not going to justify what you've done. You've got to show that what you've done is following from the rules directly. So what would I do to justify my turning right? I would say, I live in a state where you can turn right on red as long as you do two things: make sure it's safe and stop, come to a full stop before turning right at the intersection. And if I can say, look, I turned right and I followed all those rules, then my turning right at that red light is justified. Do you see it? Now, even more directly analogous would be citing theorems in a mathematical proof. You would say, I can take this step because this theorem allows me to. Well, notice, as we get good at this, we are not just going to think that makes sense. We are going to think with the rules. We are going to say, I did this rule because, I made this step because this rule allows me to. I am following the rules. We can almost, in a way, sorry for this terrible metaphor, think of this as like a religious cult, or pretend you're a perfect adherent to some religious set of principles. Well, we are going to think of our rules as the rules sent from God. These are the Bible. The rules are our Bible, and we are going to obey it. We are going to try to prove things, but the only way we can get there is by following our rules. All right. So let's look at our rules. So make sure you have out your handout, right? Good. And so let's look at the first page of the 2-page handout. We will start with the elimination rules. Here is what we are doing with each rule. These rules are telling us the steps we are allowed to make in our proofs. When we are thinking line by line in SL, it is the rules that let us move from one step to the next. I can go from this idea to this idea, and as long as I follow the rules strictly, I know that each line is logically perfect, and that's how we will think. So what we want to do first is we want to think that how are we going to use these rules in practice while we're producing our proofs. So the very basic idea is, when do we use each rule? Then we want to make sure we understand why the rule works, right? Does the logic make sense, so that if you do get stuck, you can think, okay, this is why this rule does work, and so now I know better how to use it. And then finally, and maybe most importantly, we want to get good at using the number of lines to justify the rule. So let's begin, just as a basic example, with the very first rule on our handout. Now notice, these handouts are set up to where our first page are all of our elimination rules. If you notice, when you look at the bold version of the rule in its symbolic form, it is just one of our connectives followed by an E or an I. So notice, get familiar with these rule sheets. This is your Bible. These are your commandments. You have to follow these. So you'll notice that the first page are all E rules. What does this mean? These are elimination rules. These are rules that allow you to take a sentence apart. They allow you to take pieces out of a sentence. You have a connective sentence in SL. These rules allow you to take from it. If you turn the page, you will see they are the introduction rules. When do you use those? When you want to introduce a new connective. If I need to create a new and, a new or, a new conditional arrow, I would use the I rules. When I need to take apart an or, take apart an and, take apart an arrow, then I use the elimination rules. Do you get it? So we have an easy way because of these rules. Now let me pause and let me show you how great these rules are. If you were using the more popular rules for deductive proofs, you would have rules that are much harder to remember than these. They are not organized neatly into 2 types. They don't give you hints like mine do as to when to use them. And by the way, the smallest list of rules is what? To be complete, like 26 different rules. We only have 10. And those rules are based on things that are really hard to remember. You have what? De Morgan's Law, modus ponens, modus tollens. Yes, a lot of them are in Latin. And so you have to memorize these in a very different way. For us, they're easy to memorize because what are they? They are simply our 5 connectives. Each connective has an elimination rule and an introduction rule. So really easy to remember. 5 connectives, an E and an I rule for each one. All right, so what we'll do is we'll really take our time with the very first rule, and then I'll go over them a little more quickly. And then, of course, our next video will show you how to use them. So again, this is just theory. When we get to the examples, that's when you need to make sure you understand the sheet. So let me show you what the and E rule shows in its 2 windows, left side and right side, and then we'll go a little more quickly. So first one. So notice we will call this is the and E rule. Now what does that mean in English? That is the conjunction elimination rule. But and E is fine. When will we use this rule? Review. We would use this rule when we want to take apart an and. That's the idea of eliminate. eliminating an and or taking it apart. Now notice how it works. And we use this rule in my earlier pi example. Notice what it says. If I know that Jeff is immature and short, then I can deduce that Jeff is immature. I can also deduce that he's short. If I know that we are going to the movies and going to dinner, then I know we're going to dinner. I also know that we're going to the movies. Notice, because that and sentence is true, and notice, we have to know that that and sentence is true, then I know that either side of that and can be taken apart, can be taken off that and used by itself. Now, just as importantly is the right window. The right window is to help you use this rule in practice while you're producing proofs. So on each of these rules on the right side, I produced a little mock version of what it would look like in practice. Of course, it's just really short. There's nothing else going on. We are only using this rule. The most important thing is note how many lines of justification are needed to use the rule. So if you look at the top of that right window in the and E rule, you will see I have a 2-line little proof. In the first line, I am given the sentence A and B. Now notice, that is just given to me. That has to already exist in my proof or be one of my premises. But if I know that sentence A and B is true, what follows? A. If A and B is true, then I can take A out of it. I could also take B out of it. But here's the important thing. I can only make that move from line 1 to line 2 if I give the rule and the lines above it that justify it. So, in line 2, A is true because I use the and elimination rule and line 1 is true. Because A and B is true in line 1, then A is true in line 2 because of line 1 and the and E rule. Do you see it? So that's what I'd have to do on a proof. Now notice, of course, this might exist in some long proof. This might be step 13, right? But notice, if line 13 said A and B, in line 14, I could take A out, as long as I know that that is true. Now notice, in that proof, what would we write? If we're in that line where I'm on line 14, I would say line 14, A is true because in line 13, I can use the and E rule. Good. All right, so try the next ones. Now, we will skip the or E rule. We will skip the next one down because that requires assumptions. We'll move those to next week. But look at the arrow E rule, the conditional elimination rule. Now notice how it works. If I know a conditional is true, and I used this in my pi example already. If I know we are going to dinner, then I know I will get pi. So notice how it works. If I know a conditional is true, if I know that an if-then sentence is true, what do I know? Well, I know that if the left side is true, then the right side has to be true. Notice, this only follows if I first know the conditional is true and I also know the left side is true. Look at the example I give. If Jeff talks about rednecks, then he is a comic genius. It's not really a true thing, but let's just say it is. Let's assume it as a premise. Well, then if Jeff talks about rednecks, then we know it follows that he's a comic genius. Do you see the idea? And notice when we go to the right side on this one. This requires 2 lines of justification. In order to take the right side of a conditional, I have to know 2 things. I have to know first that the conditional, the whole conditional is true, and I have to prove that the left side is true. I cannot know that the right side is true unless I first prove the left side. Think of my pi proof. Again, I know that if we go to dinner, then I get pi. And I also found out that we're going to dinner. Because I know those 2 things, I now know that I am going to get pi. Because I know the conditional is true, if dinner, then pi, and I know that the left side is true, we're going to dinner, then and only then do I know the right side is true. I get pi. You get the idea? Next one. This one you will love. This is the negation elimination rule, or the squiggle E rule if you need. This one you like. What does it mean? It simply allows you to take apart a double negation. If not A is true, you know that that has the same truth value as A by itself. So if anywhere in my proof I see a double negation by itself, not X, not B, not whatever, I know in the very next line I can simply take the double negation away. I can take away a single negation. You know that changes the truth value. But we do know that not A has the same truth value as A. This rule allows it. So notice my little fake proof on the right side of this chart. Line 1, not A is true. That's given to me. I have to show that is true first. But if I know not A is true, then I can simply in the next line assert that A is true by itself because I use the line that contained the double negation and the not E rule. Do you see it? Next, the biconditional elimination rule. So I'm at the bottom of the first page of our rules, the last of the elimination rules. Again, when would I use these? When I want to take apart these connective. So if I have a biconditional that I want to take apart, I know I should use the biconditional elimination rule, the double arrow E rule. How does it work? I would follow its steps. It tells me that if I have a biconditional, I can take it apart into its component pieces. Notice, if I have the biconditional, look at the right side, A biconditional B, I can immediately turn it into two mirror image conditionals connected by an and. Notice, this one is almost like voodoo. I am simply, but notice what it means. That is just what a biconditional entails. If you know that a biconditional is true, then you know that both of those conditionals are true, and that's what the and means. Both of these conditionals are true because this is what follows from a biconditional. So, when you need to take apart a biconditional, you will use that rule. Next page. Again, I know this theory seems fast and seems difficult. You will get it down as we get to our examples. But remember, these rules allow you to make all of the moves in our deductive proofs. You cannot make a move in a deductive proof unless this rule tells you to make that move. Each step will be justified by a rule. All right, so go to page 2. Now notice if you look at the page, there will be two rules here. The arrow I rule and the negation I rule that we are putting off till next week because they require assumptions. They are a bit trickier. So let's look at our first rule on the top of the page. This one will be completely intuitive to you. Look at it. This is our and I rule, or our conjunction introduction rule. When do we use it? Well, we want to create a new and sentence. This one is really easy. The idea here is that if I know that two sentences are true, if I know that we're going to the movies and I know we're going to dinner, then what do I know? Well, then I know that they're both true. If A is true and I know that B is true as well, I can create the new sentence A and B. Look at how it works in a proof. In this very small proof, if I know in line 1 that A is true, and if I know in line 2 that B is true, then in line 3 I can say the sentence A and B is true. Why? Now notice, it requires two lines of justification, line 1 and line 2, and the rule and I, and now line 3 is a proof. If I know that two sentences are true, I can put them together with a new and as long as I justify it with this rule. Next, the or I rule. This one's a little mysterious. This one is like magic. But think of how an or works. If you're thinking back to a truth table, when is an or true? An or is true when either side or both are true. So I know that an or sentence is true as long as one side is. Sorry about this. Listen to this sentence. Here is an or sentence. You tell me it's true, if it's true or not, right? Listen. Jeff is wearing a black shirt Or Jeff is the smartest person on the planet. He's incredibly tall. He has a full head of hair. It is not receding. He is the world's greatest lover. He is a brilliant thinker. He is the greatest dad. Did you hear that long sentence? Is that sentence true? Yes. Why? Because I'm wearing a black shirt. An or sentence is true whenever either side is true. So notice how this works. An or sentence is true as long as one side is. So, if I know that a sentence is true, I can add an or to it as long as one side is true. So notice, in the example on the right column, if A is true, then A or anything I want is true. I called it X, but X could stand for any sentence, even a complex sentence, as long as the or is the main connective. So if A is true, then A or X or anything is true based on A being true and the or I rule. Now notice we're skipping the next two because those require assumptions. Those are next week. Last rule is a biconditional introduction rule. When would you use this rule? When I need to create a new biconditional. Now notice how this will make sense because of the biconditional elimination rule. How do you create a new biconditional? Notice, it requires quite a bit of work. You can only create the biconditional when you have two mirror image conditionals connected by an and. You have to have those two precise conditionals connected by an and to create their new biconditional. In this case, A conditional B and B conditional A, then I can create the biconditional. We'll need to see this one in practice to get used to it. But that's it. Now, last point. The most important thing after using the appropriate rule is justifying it correctly. I have given you a little hint. Notice, each of these rules requires a certain number of lines before it can be used. It requires a certain amount of context. If I am using the and introduction rule, I need to first prove that each side of the new and is true. If I'm creating a new or, I need to first show that one side of my or is true. So, an important thing to note is how many lines are required to use the rule. If you look at the sheet, where I have put the rule in bold on that left side, I have also in parentheses listed the number that shows you how many lines are required to justify it. So if you're looking at the and I rule on the second page of the handout, see it says number 2. It requires 2 lines of justification. If we go to the other page, the elimination rule, and you look at the and E rule, notice, and E only requires 1 line of justification. Only requires the and that you are taking apart to justify it. So if you're going down the page, so let's look at the elimination page, you will see and E requires 1 line, or E requires 5 lines, conditional E requires 2 lines, and so on. So when you are doing these proofs, that tells you how many lines are needed before you state the justification. So again, go back up to our and E rule. It required 1 line of justification, and then I could use the and E justification. I know that sounds tough. You will see it's not so bad when we get to the examples.